All right, what's up, guys? I'm Andrew Leach. I will be covering balancing trees today for your exam two. We're going to cover AVL trees, two-far trees, red-black trees, and overall time complexities with regards to those trees. This set of reviews, there's probably maybe 4 or 5, I think. I'm going to try to make this one brief because obviously balancing trees is not the only subject that you guys need to know for the exam. But like I said, I'm going to try to make this kind of brief and explain it, which kind of brings me to my next point, right? A brief note, these slides are just going to try to focus on key information for your exam. These slides are available. I'm sure you can view them right next to where you're seeing this video. And you may have even seen the slides before the video. But either way, you don't have to sit and watch through this one. It will be longer than I made a linked list review. It will be a little bit longer than that, just because I think this one has about 60 slides or so. But anyways, yeah, a lot of the visualization of operations we do on these trees, like insert, erase, it's not particularly erase, but rebalancing, you'll see what I'm talking about. That stuff I've kind of put for some things like AVL trees and 2,4 trees, but for other things, I have a reference for those links, which is going to be seen in our future things. So I'm going to actually get a timer started here because I want to kind of keep track of time. Okay. All right. Yeah. So we've got some pictures of trees. I had a friend the other day. He told me about this thing. I never saw it. So I Googled some pictures for you guys. Yeah. Okay. And then we'll kind of go into balancing trees at this point. So if you guys remember, for our binary search tree programming assignment, we kind of ignored balancing, right? We just kind of, some of you realized that, hey, we're not, these trees can technically kind of approach this right here, this non-balanced tree. It's not really, balanced. So that problem we're kind of dealing with, I don't know why I just went out of, sorry. That problem we're kind of dealing with, we're gonna find the solution rather, which is seen in balancing trees. As we insert into these balancing trees, we see that they will rearrange themselves to maintain a balance. And the point of that is that we will maintain the properties of binary search trees, which are going to be what we have here, right? A left child is less than the parent and the right child is greater, so on and so forth. The 3 balancing trees you will learn and have learned are AVL trees, 2,4 trees, which are also called 2, 3, 4 trees, and red and black trees. I kind of left a little point here. You can look at that on your own if you would like to. It kind of just explains why we're trying to balance trees or why we have balancing trees. And you can just kind of read that if you would like with the slides associated to this. All right, going on to AVL trees. AVL trees are kind of characterized by this idea of calculating a balance factor by taking the height of the left tree and doing that minus the height of the right tree or subtree, kind of as we have here. And that is our specific balance factor. So based on that balance factor, we will decide to perform rotations as per insert or modification of our AVL tree. Right here, I have provided some reference slides. These are, I believe, maybe last semester or semester before slides for AVL trees. They're really good. If you want to visualize, you can look through these. A lot of the material I have here covers most of that, if not all of it. But it's just another way to see it if you would like. If you don't know where to start with AVL trees and you haven't even looked into balancing trees, maybe consider this video here. This is just some YouTube video I put. It's just a personal favorite of mine. You don't have to do anything like that, but it could be helpful. Anyways, talking about balance factors, right? So right here we have this big red arrow, so I'm not going to point to it any more than that. But we have a balance factor for our root node 33 calculated as 1. I'm going to explain how this is calculated. So if our balancing factor, as I described earlier, is calculated for any given node as the height of the left subtree minus the height of the right subtree, then for this 33 node, we should calculate HL as this, right? We want to find the maximum length downward. So we see 1, 2, well, we don't worry about that. We go 1, 2, and 3. So the height of our left subtree is 3. And we go ahead and say, okay, that's 3. And we should go then look at the height of our right subtree, and we see, okay, 1, 2, 2, right? So we have 3 for HL and 2 for HR. 3 minus 2 is 1, which decides our factor for this. And for this -1, it would be 1, and then 1, 2, and that would be -1. And the reason we're calculating these balance factors is described here, and that relates us to rotations. Whenever our balance factor is outside of the inclusive range of -1 to 1, meaning if you have -2, -3 to -infinity, or 1, 2, 3, it shouldn't go to infinity. It should, as soon as you get 2, you should know to rebalance your tree, right? But just in terms of theory, -1, 0, and 1 are your values that indicate a balanced tree. Now, you'll note that this is not actually perfectly balanced, right? The goal of AVL trees and balanced trees is to approach a perfect tree, which is basically this binary search tree right here. And the reason we do that is explained here. I'm not going to spend too much time. We're going to go into rotations quickly. There's 4 types of rotations, right? We have our single left rotation, we have our single right rotation, double left, and double right. Now, for these rotations, how you choose to visualize them can be very important in understanding just like the intuition behind why you do a rotation, what that looks like, and what nodes do when they follow those. All right, moving on. Yeah, the bigger picture is something I wanted to kind of cover before I go into the example, which I have here for all the rotations. When you think about a single left or single right or double left, double right, it's really only 1 or 2 operations. And so that might lead you to think, how can we balance an entire giant tree that's maybe just as big as this or even bigger, right? Like this. How does that come together to balance it? Well, don't think of it in the big picture, right? Think of it incrementally, or rather, the big tree we get towards the end is actually the process of a incremental insertion of nodes that every time we insert, we calculate our balance factor and check to see if it's out of that range. And if it is, then we need to perform these rotations. And we will see the different forms of those rotations. And this actually means we actually are maintaining the balance of our entire tree by the end of insertion with just that 1 or 2 operation of, either single left, single right, so forth. We're just doing it many times. All right, so to start with our single left rotation, we're going to say this is our unbalanced tree. It moves down, right, from A. This is our root node. And we notice we inserted C. Right? Before, this would have been balanced. If it were just A and B, A would have been 1, B would have been 0. But we insert C and we find that it's out of our -1 to 1 range. Because it moves down to the right, we see that if we perform a single left rotation, which is represented here, that our tree will then be in this state, or our balanced state. Now, I kind of see it as a string pulling over A and downward, kind of like that's our pivot almost. Maybe our pivot is B and you're pulling down A, however you see it, right? But it can kind of help to imagine you're pulling down A, and A follows down, and B stays, and C stays. After we do that, it's balanced. Moving on to single right. Again, there's a balance factor of 2 outside of our range. Our unbalanced tree is actually, as before, where it was down right. I sound like I'm talking about cheat codes for video game. This one is down left. And we notice that if we perform a single right, which is described here, where we pull kind of this whole thing over C and downward, that we will be in our balanced tree state where the height or the balance factor for each node is 0. And that's actually ideal, right? In the case of, I keep referencing this, all the balance factors would be 0. And you could calculate that yourself, right? Maybe practice that if you don't quite understand it. Just look at a tree or some binary search tree and look to see if it's balanced. The ideal is 0, 0, 0, right? But it doesn't have to be. All right, now we're going to go into double rotations. Double rotations, I wanted to briefly, before we covered, note that they require 2 single rotations. So that's why I put double left, double right. And that's also why I put, maybe a left, right, right, left. That's why I have double left / right left, because you're really doing a right then a left. So we look at our double left. we're really doing a right rotation and a left rotation. So the problem is, as where before we had right, right, or left, left, now we have either right, left, or left, right. So we have right, left, right, left. Because we have right, left in this double left case, we're going to need to essentially first get it in a state where it's right, right, or left, left. In this case, it's right, right. And after we do that, we can then perform one of those single rotations that we learned just a few seconds ago. So I imagine there's a nail kind of here, or a pivot, whatever you would like to describe it as, and you're going to pull these nodes kind of around it, meaning A is going to stay the same because the only nodes that can move are C and B. We're going to pull this C down. This C goes over the string and down. And maybe you even see it better as this, however you see it. And you can always just look at references. There's plenty of resources online. So we'll pull C downward, B follows, and we're left in a state where C is here, B is here, A is here. And as I mentioned before, that has only completed one part of our problem, right? Which is that we now have a right, right, or a left, left. This is just right, right. And from there, we can just do a single left. And that is the same as pulling a downward or B or however you see it. And after we do that, we're going to be left with our A, B, and C nodes. Yeah. Pulling our string. Yeah, pretty, seems kind of a little bit weird, but it makes sense. There's some weird specific cases to get into later. In this case, we have a form where, yeah, it's basically the same as before. We had right, left. Now we're dealing with the case of left, right. Because if you think about it, you have 4 permutations. You have left, left, right, right, left, right, and right, left. So now we're just going to deal with our left, right case. So our left, right case is going to require us to kind of put our nail between the root node and A, at least the way I see it. And I'm going to take this string and I'm going to pull it down. Or I'm going to pull A. Maybe I attach a string to A. If I pull A down and this nail is here, then B is going to move up here, A is going to move down, and C is not going to move because there's a nail between them. And if we look, we actually see that that's exactly what happens to our tree after performing this left rotation. And we get C, B, and then A, left, left. And because this one is right, right, because this one is left, left, we see that all we need to do is perform a single right rotation to fix the tree's unbalanced state. And if we do that by pulling it over C and downward, we find that it follows and leaves us with our balanced tree. Okay, this is an important point. I'm probably going to bookmark this part of the video. I guess I'm going to say 1128 is pretty important. All right, yeah. The concept of building an AVL tree with given values and performing those balances as necessary is a very extremely important. I bolded it, underlined it. I don't know if that's italicized, but usually I like to do that. You know, I can't really say much more than that. Just understand that. And more specifically, what I mean by that is if I give you n values, you know, just a line of values to be inserted, can you construct that tree and balance it whenever necessary? If you construct that tree and balance, right, as you need to, how many rotations did you have to do? And more specifically, what types of rotations did you do? Let's say I asked you how many single left rotations did you do? How many double right rotations did you do? Also, you should know visually and definitionally what rotations are, what they need to, like, sorry, let me rephrase. What rotations need to be done and what they are. So what I mean by that is you have a single left rotation, right? What does that look like? And why do you do that? Let's say I show you a tree before a rotation and after. You should be able to tell me what that rotation is. And you should also be able to tell me if I give you a tree that's in an unbalanced state and not the after, you should be able to tell me what we need to do to give that a balanced state, whether it's double right, double left, single right, single left. I inserted. I put some AVL tree slide reference notes. I'm actually going to briefly cover these because I think they're actually pretty useful for the sake of this. And I just wanted to go through them kind of briefly. Yeah, so just a build example. And this is kind of, if you already understand this, you can kind of skip past this part. But we're just going to build this in order. incrementally. We start at 13, balance factor in the top right of 0, 17, 20. Okay, our first problem is that we now have a downward right case. And so we're going to need to, and more importantly, this is -2. We're going to need to do a single left rotation around 13, which is essentially going to pull these nodes through the string downward. 13 is going to move down, 17 and 20 remain where they kind of are. And we'll be left with this balanced tree. Continue inserting. Okay, we get to a problem where we have this tree of a balance factor outside of -1 to 1 for 2 nodes. And you might be tempted to say, okay, let's try to kind of pull down this whole thing and deal with it like that. But you should really look at the lowest level balance factor first, lowest height, and you should deal with that one. So in this case, we have this, if we just get rid of this 17 in our head, we just see this kind of 13, 9, 8. It resembles our left case, which means we're going to need to do a single right around that. And if we pull 13 down, kind of don't connect 17 and 20 in your head at all, we're going to be left with 13 pointing downward, 9 in the middle, and 8 there, and our tree is balanced again. Now we're going to insert 5. Oh, we're going to insert 1. We insert 1, and we see that our balance factor, fortunately this time not for 2 things, is outside of our range, and we're going to need to balance this tree. Yeah, briefly, this part is a little bit confusing, and that's kind of why I wanted to cover it, because going from this step right here, going from this step right here to this step is kind of confusing. Or sorry, this step to this step is what I meant to say. So this one is a single right, but we're pulling a lot of nodes. We're pulling a string that pulls 17 down, and we're going to move it to here, and we're going to keep 20 there. 9 comes up here, followed by 8 and 1. But if you notice, this 13 almost just like, I won't say travels, but our 13 almost travels this direction in a way. And it's kind of hard to see, but understand this case and understand why this 17, it's swapping with the 9, and then we're pulling the 13, 17 downward, and it's happening in such a way that the 13 and 17 will end up like this. And that can be kind of confusing, and it might even help to see it as, hey, at least we know we pull the 17 down, the 20 is still there, and we have 9, and 9 must be to the right of 13, or sorry, 13 must be to the right of 9. So that can be a little bit odd, but just understand this test case. Write it down, take note. For this case right here, we're going to need a double right to deal with this too. Pull that way, so on. Yeah, and these slides are accessible here. As I said before, I kind of have them right here. I guess I'll go back into my review. You can look at those, and there's a video I provided at the very start here that was pretty helpful for me. The words are a little bit different, but it's the same concept. It'll help. All right, moving on to 2-4 trees. Okay, and the reason I say they're perfectly balanced is because between all the trees, our 2-4 tree kind of, most notably by its depth feature or property, has all external nodes possessing the same depth at all times, as where in our other trees, right, if I go way back, we see these external or leaf nodes aren't exactly on the same level, right? This one's on level 0, 1, 2. If you start at 0, this one's on 4 and so forth. You understand what I'm saying? So moving on to went way too far there. Our 2-4 trees, the properties we need to look at are the properties of 1 or 2 nodes, 3 nodes, and 4 nodes. So a 2-3-4 tree or 2-4 tree has multiple nodes that have up to 3 elements within the node, and not 4, despite this line right here, which can be kind of confusing. But basically, if our node has 1 element, it's considered a 2 node. If a node has 2 elements, it's considered a 3 node. If it has 3, it's considered a 4 node. Basically, you understand that. Note that this depth thing goes there. I put a link here to some Geeks for Geeks thing. It can be pretty helpful with visualizing. I guess we can kind of look at that. Yeah, I pulled like a picture from that. This was sort of helpful if you don't understand much of what I'm saying. But we're gonna look at the 2-4 tree. This is like a typo here. Construction of an AVL tree. Yeah, this is a pretty weird AVL tree, I guess, if it were one. This is supposed to say 2-4 tree. It just is a typo. But we'll just kind of ignore that because it changes anyways. All right, for insertion and overflow, we're just going to say just the same way as our AVL tree. We're going to think of creating our 2-4 tree as incremental. We're going to keep inserting. So let's do 11, 14, 19, and I'll stop for a second to explain two things. First of all, notice that we have our first node just kind of empty and we put something there, and now it's a 2 node. One element, but it's a 2 node because that's the number of pathways that it will eventually split to, called a 2 node. Meaning, what I mean by that is when we insert something, we go left or right, if that node exists. But right now there's only one node, so we just keep populating it. Populate 14, 19, 25. And here's our problem. If you notice, our node becomes 2 node, 3 node, 4 node, but we just put a 4th element in our 4 node. Does that make it a 5 node? I don't know. I don't think so, because what did we say here? Possessing up to 3. So between 0 and 3, but typically just 1 to 3. So what are we going to do about this? Well, we're going to have to introduce the concept of overflow, which is basically what we've done here by putting this 25 here. Overflow means we've inserted a 4th element into our 2-4 tree node. And to deal with this, we need to take a concept of promotion or splitting of the 3rd element, which is the semantics that Dr. Lake uses. There are differing methods and approaches to developing a 2-4 tree, but Dr. Lake presents the promotion of the 3rd element specifically. So that's what we'll do for this this class. This order is a little bit confusing. The way I see it is we're going to take 19, it's our 3rd element, and we'll split this 2-4 tree into 3 things. We have the numbers before, and the numbers after, and then the number. 19 is the 3rd digit, 1, 2, 3, 4, 3. We move 19 up, we promote it, and then the left subtree of that new promoted node. So there's a new node with just the value 19 here. We'll go to the left. To the left of 19 are the values 11 and 14 because they're less than. And the value to the right is 25 because it's greater than. And that's exactly what we see here in this slide. So at this point, we are good to go. We dealt with our overflow issue. We have a 2 node here, a 2 node here, and a 3 node here. Everything's good so far. Let's continue inserting. Insert 1. And before we get to our next overflow, as you saw, I want to note that I'm not just randomly putting these nodes in, right? 1 is going here because we're doing a Boolean check. Well, the computer is, right? We have 19. We go to insert 1 and we say, is 1 less than 19? That's what this arrow represents. 1 less than 19. And this arrow represents the possibility of 1 greater than 19. And that returns false. So we return true and we end up putting in bold here. We've just inserted 1. That's fine. But 3, it's less than 19. We go here. Now, here's our issue. Overflow again. What will we do? We don't know what to do. But we do know what to do, because we're going to have to look at our 3rd element just as before. You'll see it's not very exciting. It's going to be the same thing, but just it looks a little different every time. We're going to promote it. We're going to move it up, but we're not going to move it up to a new node. We're going to move it up to the parent node and add it to this. We're going to put 11 here. Now we have 1, 3, 14. And we're going to get this state. But this is a little confusing because how did that 14 just like go there? Before, when we split it, it went to the right. You might think, oh, I guess it goes to the right. But here's how I think of it. We move the 11 up. We're stuck with 1, 3, 14. After we have 1, 3, 14, we need to move the 14. Now, the only way we can move the 14 to make this balanced 2-4 tree still valid is by following this this Boolean expression check, which I kind of described earlier. 1 and 3 are less than 11. That's true. 25 is greater than 19. That's true. Now, what do we do about 14? Is 14 less than 11? No. Is it greater than 19? Well, no. The problem is 14 is between 11 and 19. And because it's between, we can think of this arrow as the Boolean for 11 through 19. That's what values should be there. And that's why we place 14 there. So it might even help to just think of just promote this 11. After you've promoted it, then we can go ahead and worry about what we do with these values, right? Do we leave it there? Do we move it? We'll see that we end up moving it in this case. All right, so, excuse me, we have overflow again after we add these two values, and it's within the bottom leftmost node. We're going to go ahead and I also want to note, we put this 18 here because 18 is not less than 11 again, not greater than 19. It's between them. So it goes there. And that's a good way to make sure your 2-4 tree is still working. Yeah, we're going to go to our 7. We're going to see we have an issue. We have another question mark node. What is it, a 5 node? Not possible. So we're going to go ahead and do the same thing. We promote this 7. Or sorry, I meant to say 5. We promote 5, and this is going to be in order of least to greatest, 5, 11, 19. But the issue is now we have a 7 to move, just as we did before. But where do we move it, right? And a good thing we can look at, I'm going to go way back here, is this thing right here. So we have a 4 node now. I believe it was maybe 5, 9, and 19. No, 5, 11, and 19 probably. I don't remember. But the point is, yeah, I think it's 5, 11, 19. Anyways, the point is the left one is whatever's less to 5. This one is between 5 and 11. That's the node it goes to. And this one is between 11 and 19. And this one's greater than 19. So that's kind of a useful thing to do. That was kind of hard to remember. I hope it was 5, 11, and 19. Yeah, so that's exactly what we have. And that's kind of talked about in here. The reason we're going to go ahead and say 7 doesn't belong here is because, well, 7's not less than 5. Is it between 5 and 11? Yes, it is. That's exactly where it belongs. And so we're going to create our 4th node, which makes this a successful 4 node. 4 node, as I said before, is denoted by the number of children, 4. We're going to insert 96, and technically we're done at this point. The problem is, I would like to, or sorry, not the problem, but I would just like to kind of insert some more values in order. I'm going to insert 2 at a time. If we insert 27, it's not going to cause an overflow. But then we're going to insert 69 after that. And we're going to see that causes us an overflow. So my question is, what are we going to do? Well, you guessed it. We're going to promote the 3rd element again. We move 69 up. And it can be helpful to see it in its own thing. You could move it up here, but I'm just going to say for now, move 69 into this. But the issue is we moved 69 into this and we just got another overflow. And I didn't draw that and it probably would have helped. But just imagine we put a 69 here. This has an overflow. So we need to then split this and promote the 3rd term of 5, 11, 19, 69. 19 goes up. 5 and 11 go to the left, and 69 goes to the right. Well, what are the children of 69 now? Well, 69, what goes to the left of 69? If you're talking about 25, 27, and 96, what is less than 69? Well, it's 25, 26. So we have a 3 node going to the bottom left of 69, and a 2 node going to the right of 69, which is 96. And that is kind of visualized here. It can be a little confusing, but I'll say one thing. The reason our 1, 3, 7, 14, 18 go to the same node, like here, and not like 14, 18 isn't to the left of here, is just kind of look at this 2-4 tree. It's valid and it has to be. That's because let's kind of break it down recursively. First, we check less than 19 because it's just a 2 node. Value's 5, that's less than 19. Okay, cool. Value 11, yeah, that's also less than 19. We look at 1. Okay. 1 is less than 5. That's good. 3 is less than 5. That's good. So we definitely put 1 and 3 in the right place. 7 is not greater than 11, but not less than 5. Okay. Oh, yeah. We need to put it in the middle here between 5 and 11. 14 and 18 are greater than 11. So let's go ahead and make sure to put those to the right of 11. And you're saying, okay, well, why don't we put 14, 18 here? It's true that 14 and 18 are less than 69, but the problem is they wouldn't even get there in the first place if they're not already greater than 19. So what I mean by that is, look, we have 19 goes to this, goes to this. Now, the issue is, if we were to get rid of this 18 in your head, if I put an 18 in, is there any way it would ever go to the right at any point? No, it wouldn't. And so that's kind of the beauty of 2-4 trees, is we're actually establishing something like this without even necessarily thinking or realizing it. But we know now that this value 18, no matter where it is relative to this, will always be less than this. And it will always be greater than this. And that's kind of just another property of binary search trees that we know. But that's kind of a good way to understand, is my 2-4 tree correct? Am I doing this right? So that's kind of a good way to do it. It can be rough, but just draw it out. I know I kind of skipped a few steps here. Tried to explain as best as I could, but please draw them out. All right, talking about red-black trees. So I'm just going to go over the rules, and there's some visuals here that I provided, and I might briefly go over those. I'm not sure what we're doing on time. So first of all, the root is always going to be black. So 13 here is black. It's a black node. The second rule is no red node is going to have a child or parent that is also red. So for example, what I mean is 8. If we look at 8's child, it's not red. If we look at 8's parent, it's also not red. That is a rule or requirement of a red-black tree to guarantee its validity. So the path from the root to any black leaf node should be the same for all paths to any given black leaf node. Now that's kind of wordy. I'll just kind of show you. It's very important to understand this visually. So we have our root to any black leaf node path. So 13 to, say, 1. It happens that all the other black nodes other than the root are in this example. So I might actually use the next slide's example, I think. But also, before we go on, this third rule is described typically as black height. And so we'll look at black height here. We'll say, okay, total number. Yep, okay. So the total number of black nodes on the given path from the root to the black leaf node, including the root and leaf, is going to be your black height. But before I do that, I actually want to finish what I said here about the path. The path is, what I mean by that is, we start at our root and we go to any leaf node. 12 to 5, well, that's not a leaf node. We need to do a path of like 12, 5, 3, 12, 5, 7, 12, 5, 11, 12, 5, 13, or 12, 5, 17. Sorry, 12, 15, 13, or 12, 15, 17. All right, so to calculate our black height, we're going to say, and first of all, the requirement of this right here is that this path should be just as long here to here. So there's no 12, 5, 3, 2, because of the black height being calculated as we'll see as 3. So the root is 1. We're going to do 12, 5, 3. That's our path. 12, 5, 3, 1, 2, 3. Okay, yeah, so 3. And let's just test it. Let's make sure this tree meets it. We'll do 12, 5, 7. That's the path from a root to a leaf black node. That's 3. 12, 5, 11. 1, 2, 3. 1, 2, 3. 1, 2, 3. We find that all paths from a root node or the root node to a black leaf node or external node are going to be 3. That's the count. Because it's 3, we find that our black height of the tree is 3. And this is something we can compare to the actual height of the tree. If I were to ask you, what is the height of the tree? What is the black height of the tree? Just understand what that means. All right, so when we're inserting a node, kind of as you did for 2-4 trees and AVL trees, it's always inserted as red. The 3 cases of insertion is kind of the same thing as what we're doing as maybe rebalancing, or for a 2-4 tree, I suppose, promoting. It's going to be dealing with the case 1, 2, and 3. The first case here is going to be recoloring. So for a recolor, if you insert a node with an initially red parent that has, now this should say an initially red parent, which has a red sibling, which means we're inserting 6, our parent node is 10, and 10's sibling is 20. That means they're both red, so we need to just recolor. By recolor, we're not going to recolor 6, we're going to say flip. There's only 2 colors, so think of recoloring as just flipping the color. 10 goes to black, or sorry, this red goes to black, this red goes to black, this red goes to, or black goes to red. But we didn't change the 6. Now, notably, this is because we are only supposed to swap the colors of the siblings, the parent sibling like pair here, and the parent of those two. And this is kind of one of those things you see in a perspective like this, and you go, oh, I might be doing the entire thing up to the root. Well, it's actually just supposed to be these two. All right, and please look at, I don't know where I put, yeah, these visuals. Go look at these. They're really useful. I mean, just to be completely frank, you should really look at what it takes to build stuff like that. But I'm going to continue on here. So, all right, black hide. Yeah, case 2 is a double rotation where our goal is this 15, 10, 17 state, and this is what we have. Also here, I didn't mention this. This should go to black because it's also the root. So when you recolor and the root is ever turned to red, make sure to turn it back to black. I forgot to note that. That's a very important part. There's some cases where it's not the root node, but you should if it is the root node and you recolor it. If you insert a node and it has a red parent and a black sibling, which is null in this case, we consider that as a black sibling to 10. If the inserted node is 15, we look and we kind of have this, it looks familiar. Left, right, that's an AVL tree, left, right. We actually need to perform a double rotation. So we're going to kind of do what we did before. We pull this 15 down, do our left rotation, and we're left with 17, 15, 10. And from there, we have what's considered, you'll see it later, you'll see the next slide. It will make a lot of sense when I say effectively case 3. We'll move this down, and we end up with a state where we have 17 pulled down, 15 and 10, and we make 15 black because it is the root node. And interestingly enough, I'm almost tempted to say that this might be an error. That this should be black and this should be black. But anyways, moving on. If you have a red parent, depending on what we'll do, single left, single right. Yeah, okay. So this is case 3. This is this. 17, 15, 10, null. We're going to rotate this downward to a state where it's this. Yeah, see, this is what I was saying. This is very odd. Okay, 10, 15, 17. Yeah, we pull this downward and we get a state where we have 10, 15, and 17, and we need to recolor. Yeah, that's kind of a part I shouldn't have skipped when I explain this. The reason I say it's odd is we have to recolor our tree, right? As follows. And looking at these notes for comparison's sake, we see that it's very similar. So, and to be honest, these notes that I reference, I tried to make them, I mean, there's not much variety in terms of making a presentation of red-black trees. There's 2 colors you get. So they're very similar and they're very good presentations that I reference. I'll leave it at, go look at this, like actually go look at this and understand what this is doing, because you need to understand this. If you already understand it, good, you're Thanos, you're chilling. But, you know, if you're not Thanos, then please look at this and what's happening, because I'm sure at some point what I was talking about here probably got a little confusing. It honestly even got a little confusing to me just because of the fact that I didn't articulate this point. But point is, go look at this. It's very useful. That's pretty much the reference for these 2-4 tree slides. We'll go back to our slideshow and we'll talk about something I basically just talked about, which is the importance of constructing red-black trees. And also note, what is the number of comparisons for building a red-black tree with n items? We should be able to know that if I were to ask you. Now, this is the point of the video where I'm going to cover kind of some additional notes and just some more specific stuff that you should understand generally. I'm going to put a bookmark here. This is kind of the double asterisk stuff we see here. We denote that with a double asterisk. I kind of just use that to indicate that, hey, the other stuff is really useful for your exam. But if you had to take the exam in 20 minutes, like your exam starts in 20 minutes, then you should go to this part of the video and you should make sure to get these points down. All right, so we will look at big O here and say, search. Search is the most important to me because in my eyes, intuitively, the reason our other complexities will be what they are is we have to search. To search where to put a node, it would be O of log n, just as any binary search tree. That's kind of the whole point, right? And as well as that, what's the time complexity of finding a max or min value? Well, it should also be O of log n, because when we have a max or min value in our binary search tree, well, in our homework, what did we do? In our PA, what did we do? We moved all the way to the bottom left. What did we do for the max? We moved to the bottom right. In our red-black tree, specifically, it's O of log n. Verify if it's the same for all three trees. That's something you should look into. To insert, dealing with insertion, as I said a minute ago, we need to know where to put that node. That's O of log n. And now don't get this mistaken with what it takes to insert n nodes. Right? To insert n nodes, it would be log n to search. So let's say we have n nodes. First node, we need to look where to put it. That is a log n operation because it's a search, and we're performing that search operation one time, then 2, 3, ... n. So we're going to perform search n times, and whatever it takes to insert, create it on the heap, whatever. And we're going to connect our dot right pointer to that, or dot left, whatever it is, and we're going to do that in n log n. Log n operations n times. Deletion is very similar to insertion. To delete a node, we have to find it first. After we delete it, we'll find that our deletion is O of log n. Okay, some extra notes just in general. Make sure that these make intuitive sense to you. Like, it makes intuitive sense to me why insertion and deletion are log n. And it's not, I'm not saying you have to be Einstein. I'm just saying you should really make sense of it, right? Maybe some of this doesn't make sense to you. You should be able to make sense of that. And it's true that for our types of trees, now I do kind of, I don't know if amortize is the right word to say here. I do kind of say, oh, well, let's just say log n, search, insertion, and deletion are the same for all. But understand that there are pros and cons to each tree type, and there's reasons and test cases or use cases for all of them. And there are technically efficiency differences. And an example of that is like AVL trees, for example. You have to check for the balance factor. You have to perform a lot of operations to maintain a balanced state. But the pro of that, if that's the con, is that we actually have a now balanced and very balanced tree, which means search operations, insertions, deletions, that is going to approach log n pretty much exactly. Now, compare that to a red-black tree, where it's going to be faster and more efficient because it uses less operations to maintain that balanced binary tree state. But the problem is, like, when I say less operations, I mean it's not going to have balancing as much as AVL trees or 2-4 trees. 2-4 probably uses the most, but that's why 2-4 is the most, or one of the most, I want to say the most balanced probably. As you can see, I said perfectly balanced. I described that earlier, but we kind of need to understand, there are differences in the time complexity, but they're negligible in the case of this and our exam. But you should understand that there are different uses. All right, these are pretty important. I would say definitely go look at these slides, get out your pencil, maybe, like I said, your Thanos, you don't need to look, you don't need to do them, but these, what is it, 1, 2, 3, 4, 5, 6, 7, these 7 bullet points, I mean, I'm just saying, you should probably look through all of them and understand that you can do them. And if you can't, practice them. How long does it take to print out an entire tree in sorted order? Figure that out. Understand why. If I were to give you a specific tree and ask you, is it a valid tree? And when I say specific tree, I mean, I'm not going to tell you it's an AVL red, black, 2-4, obviously. I'm just going to show you a tree. And I'm going to say, is it an AVL tree? Is it red, black? Is it 2-4? Or is it, none? Is it just some random tree? The reason I ask this is my point is you should know these rules. You should know the definition of an AVL. You should know the definition of a red-black. Now, I wouldn't be so worried about, I'll just give you a tree and say, which tree is it? It could be multiple. But just say, if I say, here's a tree. Is it a red-black tree? You should say, no, the first node is red. The first rule is broken. It's not a red-black. If I ask you to count the number of children, or sorry, if I were to ask you to find the number of elements in a tree, given the count of children that 2-4 tree has, could you actually complete that? And vice versa. I don't know why I explained that so poorly. Vice versa, I mean, given the number of elements, could you find, and more importantly, in a 2-4 tree, could you find the count of children? These points, this point as in this point, and this last point kind of go synonymously. Is every red and black tree considered an AVL tree? Understand those conditions, and that kind of, I'll talk to this one later. Can you calculate the number of comparisons necessary to construct various trees with n elements? So are you capable of, understanding and knowing what comes into play with the comparisons for said trees, right? Do you know what comparisons are happening? Can you understand the process of building AVL 2-4 and red-black trees? Now, this entire bullet point, it's not a specific question, but it's a general thing to just kind of put a check mark on. What I didn't cover so heavily in this video was, as I said before, the insertion, the visualization. So do you understand the process of building any of those 3 trees? Do you know when you need to perform tree balancing operations? And more importantly, sorry, I guess I should switch it. Do you understand what balancing operations to perform, what they are, what they look like? And do you understand, more importantly, when to do them? Like if I were to show you an unbalanced tree and show you a balanced tree after, and I think I brought this up earlier, would you be able to tell which balanced happened for an AVL tree, maybe a 2-4 tree, maybe a red-black tree? Could you tell me what you saw? And maybe I showed you an unbalanced AVL tree and I said, can you complete this? Like, what do I need to perform? Is it a single left? Is it a single right, double left? What rotation do I need to perform on this AVL tree to then make it balanced? Is the permutation, yeah, this is a specific question. Is the permutation all red-black trees? This is kind of just, I wanted to better explain this point. All red-black trees are AVL, but not all AVL trees are red-black. Is that an accurate statement? And more importantly, if it's not, or if it is, why? And can you make a permutation that is correct? I don't know. Figure that out. I'll say this is going to pretty much be the end of our review. My clock is saying we're about 49 minutes, 48 minutes. This is it's a pretty good time considering I did 60 slides. There's just one brief thing I wanted to cover. This is probably the most important part. I'll bookmark this as well, guys. You really need to pay attention to this part. If you haven't gotten any notes out yet, or a paper and pencil, you're going to want to write this one down for the exam, okay? This is very important. You got this. This exam, your second exam of the semester, I know you guys are going to do great. I know you guys are going to be fine. You've got great TAs, you got great PTs, you got great resources. You had your first exam. Some of you did great. Maybe some of you didn't do as good as you would have liked, but you understand kind of how the game works now, right? And if you know how the game works, then it's up to you to decide whether or not you're going to train and play right, okay? Spoken like a true computer science major, I guess I don't know what I'm talking about, but anyways, my point is, thanks for watching. This is only one of 5 or 6 reviews that are being put out. It is kind of a long one. I do apologize if you guys got bored. If any of you made it through the entirety, the 50 minutes of this review, then you're pretty much like Dr. Lake's strongest soldier. I mean, I really don't know how you made it, but good job, good work. You're definitely going to do great. If you're willing to put in the work for that, then definitely good job. Like I said, the slides are available. The other slides, watch. Theory made some, Nihar made some, Sophia made some. Please watch. If you're seeing this before the weekend review, write down questions you might have specifically about the slides. Maybe these slides I wrote something really crazy and I didn't know. Just let me know. Yeah, other than that, I don't think there's really much more that I can think to say. Laker Nation, baby. You guys got this. All right, guys. Good luck.